Yes, good afternoon all my dear students. Hope all of you are fine, doing well. Yeah, as we discussed yesterday, today we will be discussing another organic chapter, that is alcohol, phenols and ether. This is also another important chapter in which is coming in the 12th class chapter. Okay, yes, so hope all of you have do their proper revision of this chapter so that now we can do this chapter very easily. Okay, so yes, so shall we start the class? Is everything fine and going good? We can start the class. Okay, yes, thank you. Yes, these are the important points that we will be discussing in the today's class. They are, yeah, alcohols, then phenols, then ethers. These are the important points in this chapter. That is alcohol. We will be particularly discussing about the, let me, just give me a minute. Okay, sorry. Yeah, the alcohol major points we will be discussing is about the preparation reaction. We will be discussing. In that we will be discussing the acid catalyzed hydration, then hydroboration oxidation, oxymercuration demercuration, then the reduction of carbonyls and Grignard reagent, and then comes the chemical reaction, that is Lucas test. Then Lucas test that we already have discussed in the previous classes, then dehydration of alcohol, then the oxidation states. All these are the points that we will be discussing in the alcohol part. Now coming to the phenol. The basic thing is method of preparation of phenol from cumene or from benzene sulfonic acid and diazo salt. And next comes the acidity of phenols. Then the name reaction. There are two important name reactions are there. One is Reimer-Tiemann reaction or RTR reaction, then Kolb's reaction. These are the two important name reactions we will be discussing in phenols. Next comes ethers. Ether is the method of preparation. Dehydration of alcohol, then Williamson ether synthesis. That are the two. This is one of the another name reaction that we will be discussing in ether. Now next important point is the chemical reaction of ether, especially the cleavage of CO bond by hydrogen halide. That is another important point we will be discussing. Okay, now we can go through it one by one. First is we will be discussing about alcohol. The first and main point alcohol is acid catalyzed hydration. Okay, acid catalyzed hydration, you have already discussed this one in hydrocarbon chapter. What is this? That is alkene. This is prepared from alkene. The first three reaction of preparation of alcohol that we will be discussing is preparation of alcohol from alkene, and the first is by the acid catalyzed hydration of alkene. And what we have to do? We have to do nothing, just follow Markov-Nikov rule. According to Markov-Nikov rule, what it is? Hydrogen will be adding to that carbon where there is more number of hydrogen, and OH will be adding to that carbon where there is less number of hydrogen. That is what Markov-Nikov rule is saying. And as a result, what I will be getting? The OH will be added to the secondary carbon and hydrogen will be added to the tertiary carbon. We got the product, very easy only. But the problem that is happening is when it's coming to the tertiary. CH double bond CH2. Okay, here you can see this is a tertiary carbon. In this case, if you do the acid catalyzed reaction of alkene, what is the first thing you have to do? The first step is shifting of bond towards the carbon, in which we will be getting a stable carbocation. Now see the stable carbocation here, CH3. Yeah, this is a stable carbocation that we got here. Okay, now we have to check for the rearrangement. And this is a secondary carbocation. It can do rearrangement and can form tertiary carbocation. RCR CH. We can form the tertiary carbocation. And next what you have to do? Next we will be attaching OH to this tertiary carbocation. Okay, so always whenever you are applying the Markov-Nikov rule, you have to check for the rearrangement. Okay, so this is the point regarding acid catalase. In acid catalase reaction, you have to go for the carbocation rearrangement. After that only you have to go for Markov-Nikov addition. Is it clear? First method of preparation of alcohol. Is it clear, Sakshi?
Yes, sir.
Okay. Next we will be moving into the hydroboration oxidation reaction. Hydroboration oxidation reaction. Hydroboration oxidation reaction, you don't need to worry about anything. What you have to do? This is also preparation. This is also the preparation of alcohol from alkene. Alcohol from alkene. And what you have to follow? Anti-Markov-Nikov rule. Anti-Markov-Nikov rule you can follow, and you can get the alkene. You can get the alcohol here. Okay. So here also same thing you have to do. Just add hydrogen to that carbon where there is lesser number of hydrogen, and OH will be adding to that carbon where there is more number of hydrogen. That is what Markov-Nikov rule. In Markov-Nikov rule, you no need to think or worry about carbocation rearrangement or not. Just add hydrogen to that carbon where there is lesser number of hydrogen, and OH to that carbon where there is more number of hydrogen. That's only the point. And resulting what we will get are CH2OH. Yeah, here is a point. Okay, and first step in this process, BH3 tetrahydrofuran. What is this one? This will be doing the this reagent BH3 tetrahydrofuran or B2H6. They will be doing the hydroboration. And who will be doing the oxidation? After the hydroboration step completed, next H2O2 will be doing the oxidation, and resulting we will be getting the primary alcohol. If we use alkene with a terminal carbon, if we use alkene having terminal carbon, then definitely we will be getting primary alcohol. Got it? And note down, this is a syn addition. We will be adding hydrogen and oxygen to the same side. That's coming to the stereochemistry only. And there is no rearrangement. That's the important thing. That's the easiest thing. No rearrangement, as it is proceeding through a cyclic transition state rather than a carbocation. The carbon skeleton remains unchanged. Okay, got it? Yes. Is it clear? The two method of preparation we discussed: acid catalyzed reaction, which follows Markov-Nikov addition, and then hydroboration oxidation, in which we will be following anti-Markov-Nikov addition. Got it? Yes. Next, moving to the next one, that is oxymercuration demercuration. Yes. Oxymercuration demercuration, we will be using the reagent HgOAc twice. This will be doing the oxymercuration, and NaBH4 will be doing the demercuration. Oxymercuration means we will be inserting HgOAc, that is mercuric acetate, into the alkene bond, and then using NaBH4 we will be removing or we will be demercurizing it, and we will be getting the alcohol. And here what you have to do, just follow Markov-Nikov rule. That's only we have to do here. Okay, so I am just checking a product RCH double bond CH. This is my substrate. What I have to do? What I will do? The reagent HgOAc twice H2O. Oxymercuration will be happening. Then the second step is NaBH4 reducing agent. Demercuration will take place. Hydrogen will be adding to that carbon where there is more number of hydrogen, and OH will be adding to that carbon where there is less number of hydrogen. So resulting what I will be getting RCH OH CH3. And here it is following Markov-Nikov rule, and there is no carbocation rearrangement here. In this case there is no carbocation rearrangement. Why? Because it forms a cyclic mercurinium ion intermediate, which prevents the cell skeletal from shifting. Because of that, we no need to worry about carbocation rearrangement. Just follow the Markov-Nikov rule completely. Okay. Yes. Got it, everyone? First step, follow Markov-Nikov rule and check for the carbocation rearrangement, that is acid catalyzed reaction. Second one, anti-Markov-Nikov rule, that is hydroboration oxidation. Third one, oxymercuration demercuration. Follow Markov-Nikov rule. In the first case only you need to check for the carbocation rearrangement. Remaining two cases no need to worry about that. Got it? Sakshi and Pranidhi? Yes. What about Pranidhi? You got it, Pranidhi? or do you want me to repeat once again? Okay. Yes. Now this is just a summary of what we discussed. Acid hydration, reagent is H3O plus, Markov-Nicoff addition. Yeah, rearrangement is there. Yes. Then oxymercuration, demercuration, HgOIC twice, NaBH4, Markov-Nicoff addition, no rearrangement. Hydroboration oxidation, BH3H2O2, anti-Markov, there is no rearrangement. Very easy. Usually you can score from this part. Okay. Moving to the next one. That is oxidation of alcohol. Oxidation of alcohol is another important one. Oxidation reactions and reduction reactions, these are very important part. Oxidation of alcohol, what I can just do is, if I am using a strong oxidizing agent, if I am using a strong oxidizing agent, what is going to happen? Primary alcohol will be converted to what? Will be converted to acid, and secondary alcohol will be converted to ketones. And what is going to happen to the tertiary alcohol? What is going to happen to the tertiary alcohol? Can anyone let me know? Tertiary alcohol.
Alkene is formed.
Alkene won't be forming all the gases. Only one particular oxidizing agent only will be leading to the alkene. That we will discuss. Okay. There won't be any reaction. In the case of tertiary alcohol, because there is no oxidizable hydrogen. In the case of tertiary alcohol, so there is no reaction going to happen here. Okay, this is in the case of strong oxidizing agent. In the case of weak oxidizing agent, how the conversion will be? Primary alcohol to aldehyde, secondary alcohol to ketone, and tertiary alcohol, there is no reaction. In the case of tertiary alcohol. Okay, now when it's coming to the strong oxidizing, which are the strong oxidizing agents? Which are the strong oxidizing agent? Hot alkaline, KMnO4, then K2Cr2O7, potassium dichromate, then concentrated HNO3, then Jones reagent, which is Jones reagent, CrO3 in presence of H2SO4, then comes, and what is next? Any more strong oxidizing agent, do you know? Any more strong oxidizing agent? Okay, these are the important strong oxidizing agent. Now coming to the mild oxidizing agent.
ACC. Pyridinium chlorochromate.
Yeah, that is strong or weak?
Weak.
Yes, very good. Mild oxidizing agent. Yeah, first one PCC, then pyridinium chlorochromate, then DCC. Yeah, then comes Collins reagent. What is Collins reagent? If CrO3 is taking place in presence of a base, that is pyridine, then it will be acting as a weak oxidizing agent. Then what about the fourth one? Fourth one is copper at 300 degrees Celsius. So these are the important oxidizing agent and reducing agent. Got it? Is it clear? Okay. Oh, is it 300 degrees Celsius or 300 Kelvin? I think it is 300 Kelvin. Okay. So these are the important strong oxidizing agent and mild oxidizing agent. Now apart from this, I want to introduce some of the special oxidizing agent. Which are some special oxidizing agent? Special oxidizing agent. First one is MnO2. MnO2 is a special oxidizing agent. It will convert. It's a mild oxidizing agent. It will convert primary allylic or primary benzylic alcohol. Primary allylic or primary benzylic alcohol to what? To aldehyde. Primary allylic or primary benzylic to aldehyde, and secondary allylic or secondary benzylic alcohol to ketone, and tertiary no reaction. Tertiary there is no reaction. This is one of the special oxidizing agent, that is MnO2. It is a mild oxidizing agent. Now coming to the one more oxidizing agent is there, that is Br, bromine water. Bromine water, another oxidizing agent. What is this? It will be converting which all reactions? It will be converting phenols. It is a special oxidizing agent. It will convert only some special substrate. First one is phenol. It will be converting to quinone, and aldehyde it will be converting into acid, and alkene it will be converting into bromohydrin or dibromine. It can convert either alkene to bromohydrin or hydrin, the compound with both bromine as well as OH group, or dibromine compounds. So these are the complete information about oxidizing agent. All the things we have discussed here: strong oxidizing agent, weak oxidizing agent, what are the categories, then special oxidizing agent which are MnO2, then bromine Br to water. What bromine water is doing? Phenol, it will convert to quinone, aldehyde to acid, then alkene to bromohydrin or dibromo compound. Okay, so this is the complete idea about the oxidation of alcohol. Is it clear? We can note down all these things. All are very important. Got it? Shall I move to the next one? Is it clear, Sakshi, Pranidhi, Vasant? Yes. Now here one more point I want to discuss, that is about the copper. Yeah, copper is a mild oxidizing agent. It will convert primary alcohol to alkene, that is by dehydrogenation, and secondary alcohol to ketone, dehydrogenation. And normally we know that tertiary alcohol don't have oxidizable hydrogen, so it won't be undergoing dehydration, or it won't be converting into anything, or there won't be any reaction. But if I am using hot copper at 573 Kelvin, okay, it's 573 Kelvin, it's not 300 Kelvin, it is 300 degrees Celsius. Okay, 573 Kelvin, tertiary alcohol will be converted to alkene. That is the point you have to note down in the case of copper, in the case of the oxidizing agent copper. Okay, note it down. Everything we have covered here. Shall I move to the next? Done, all of you? Anybody want me to repeat anything once again? Okay. Yes. Next we will be discussing about the Lucas test, the reactions. Yes. Okay. Next we will be discussing about the Lucas test. Lucas test, what is the test? It is used to distinguish primary, secondary and tertiary alcohol. Primary, secondary and tertiary alcohol, which we already discussed in lot of the chapters. Hydrocarbon we have discussed, aldehyde ketones we have discussed. What is this one? Tertiary alcohol will be giving immediate turbidity. Then secondary alcohol, they will be giving turbidity within 5 to 10 minutes. Primary alcohol, no turbidity at room temperature, or the turbidity will be occurring after a long time. But who will be waiting for this much time? So we will be considering that there is no reaction for the primary alcohol. So this is the point you have noted down in the case of Lucas test. I hope all of you know about Lucas test. And Lucas reagent is equimolar solution of certain Cl2 and HCl. Okay, done. Shall I move? Yes. Shall I move, students? Have you noted down? Done? Okay. Shall I? One more thing is there, that is the next test to detect the presence of alcohol, primary, secondary and tertiary alcohol. What is that? Victor-Mayer test. Victor-Mayer test. Note down these tests or these reactions. A more complex but definite colorimetry test. And how we can easily remember this Victor-Mayer test? Think of the mnemonics RBC, that is primary alcohol. If it is alcohol, is a primary alcohol. It will be on treating with potassium iodide and AgNO3 and HNO2. What I will be getting? I will be getting a nitric acid, and which will be forming a red blood solution, that is red color, red blood solution with the NaOH. And secondary alcohol, how it will be forming? It will be forming a blue color solution. It will be forming a blue color solution. And tertiary alcohol, there is no reaction with HNO2, that is colorless, that is B, that is what RBC. Just remember this one, so that easily you can remember the color of alcohols in Victor-Mayer test. Okay, we can just go into the first reaction, that is primary alcohol. Primary alcohol, if I am taking ROH, if I am treating with the potassium iodide, sorry, it's not potassium, it is phosphorus iodine, what I will be getting? I will be getting Ri, that is we will be getting alkyl iodide, which we have discussed in the yesterday's chapter, that is haloalkanes and haloarenes. Then on treating with the AgNO2, on treating with AgNO2, what I will be getting? I will be getting nitroalkane or NO2. And which one on treating with the HNO2? Which one on treating with the HNO2? What I will be getting? I will be getting nitric acid. RC double bond NOH NO2. This is nitric acid. This one on treating with the NaO. This one on treating with NaOH. What I will be getting? I will be getting a red solution. This is what the first method of detection of primary alcohol. Now in the case of secondary alcohol, the same step. Here I will be getting a pseudo-nitrile. In the case of secondary, I will be getting a pseudo-nitrile. What is pseudo-nitrile? I will be just writing that reaction also. Yeah, this is what pseudo-nitrile. This is what pseudo-nitrile. So that is secondary alcohol. Secondary alcohol, the same thing. Now if I am taking tertiary alcohol, there is no reaction with the HNO2. Tertiary alcohol, it will be reacting to AgNO2, then HNO2, it is having no reaction. That is colorless solution. So like that we can understand what is primary alcohol, secondary alcohol, tertiary alcohol. Just go through it. It's nitric acid and pseudo-nitrile. That's the only point you have to note down in the case of primary and secondary. And the color, red, blue and RBC. So two important method of distinguishing primary, secondary and tertiary amine, that is first one is Lucas test, second one is Victor-Mayer test. Just keep these two tests in your mind. So this is a complete idea about alcohol. Now we can move into phenols. Shall we move to the phenol, students? Guys, are you there? Shall we move? Yes. What happened? Chesta, Sakshi, Vasant. Shall we move? Yes. Yes. Next is all about phenols. Phenols, few more things we have to discuss. That is, first is about the method of preparation of phenol. First method of preparation is cumene. Cumene, what is cumene? Cumene is isopropyl benzene. Isopropyl benzene. First we can prepare the phenol from the cumene. So I am taking cumene, which is isopropyl benzene. This is what? Isopropyl benzene. This is isopropyl benzene. Okay, and this isopropyl benzene on oxidation, what is going to happen? Or this one on treating with O2, what you have to do is just insert this oxygen. Just insert these two oxygen between the carbon and hydrogen. Insert the two oxygen between this carbon and hydrogen. What I will be getting? I will be getting cumene hydroperoxide. I will be getting cumene hydroperoxide. This is what cumene hydroperoxide. Cumene hydroperoxide, and this cumene hydroperoxide on treating with the H3O plus, what I will be getting? I will be getting phenol. What you have to do is just remove the acetone part here. Just remove this acetone part and then insert the OH to the benzene. OH plus CH3, C double bond O, CH3. That is, you will be getting phenol as well as acetone in the method of preparation of phenol from cumene. That is, along with the phenol you will be also getting a good amount of acetone also. So it also can be used for the preparation of acetone also. Just follow the method how we can prepare it. That is, just insert oxygen between the carbon and hydrogen. You will be getting cumene hydroperoxide. Then remove the acetonic part there and get the phenol. That's only thing you have to note down in this point. Is it clear, everyone? Shall I move, students? Done? Yes. Shall I? Are you there? Chesta, Vasant. Vasant, from which JNV you are, Vasant? I think you are a new one here. Okay. Yes. Moving. Yeah, next is preparation from diazonium salt. Already we discussed this preparation. Already we have discussed this preparation. From where we have discussed? We have discussed in the amines chapter how we can prepare phenol from diazonium salt. We have discussed this one in the reactions of diazonium salt. First of all, NH2 on treating with the NaNO2 HCl in presence of 0 to 5 degrees Celsius. What is going to happen? I will be getting benzene diazonium salt, N2Cl. I will be getting benzene diazonium salt. That is what the diazotization process. And this one on treating with the warm water, warm H2. What I will be getting? I will be getting the phenol here. I will be getting phenol. That is a simple method of preparation of phenol from benzene diazonium salt. Got it? Got it, everyone? Then first prepare benzene diazonium chloride, then add warm water, because we know that this is not that much stable compound. It is stable only in this very low temperature, and if you give warm water, it will be losing its stability and will be converting into alcohol or phenol. Got it? Shall I move? Students, shall I move? Just give me some thumbs up so that I can make sure that you have gone through it. Hey students, are you there? Sakshi, Chesta, Vasant. Okay, yes, thank you for your response. Okay, next is method of preparation from benzene sulfonic acid. Benzene sulfonic acid, another method of preparation. That is also an easy method of preparation. That is, I am taking benzene, and this benzene under sulfonation, H2S2O7, that is oleum, or we can take H2SO4. And this one, what I will be getting? Sulfonation, the product that we are getting, the sulfonation, SO3H, benzene sulfonic acid. And this one on treating with the NaOH under heat, what I will be getting? I will be getting sodium phenoxide, ONa. Sodium phenoxide, which one on treating in the presence of acid, we will get phenol. Another easy method. Okay. Note down these reactions. Method of preparation of phenol from benzene. First it will be converted to benzene sulfonic acid, then treating with NaOH we will be getting sodium phenoxide, then phenol will be obtaining. Shall I move? Students, can I move? Okay, have you noted down the points? If that is the case, I can move. Okay. Next, the important name reaction in the phenol, that is Riemer-Tiemann reaction. It is what is this reaction? It is just introduction of aldehyde group into the benzene ring. That's only the point you have to benzene ring in the phenol. That is only point you have to note down. That is, I will be taking phenol as our initial substrate. Phenol, which one on treating with the CHCl3, that is chloroform, and then it one on treating with NaOH. Then it is on treating with NaOH. What you will be getting? You will be getting ortho salicylic aldehyde, that is CHO. That is an aldehyde group will be inserted into the ortho position of phenol, which is what we will be calling it as salicylaldehyde, which is 2-hydroxybenzaldehyde. And note down the intermediate that is forming here. What is the intermediate that is forming here? It is dichlorocarbene, CCl2. The intermediate that is forming here is dichlorocarbene. That's another point you should note down. Dichlorocarbene. Yes. Can I move? Riemer-Tiemann reaction is important one. It's an important name reaction. Remember, this reagent in which you got a phenol will be converted to salicylaldehyde. Shall I move? Are you done? Just give me some reactions. Yes, thank you, Sakshi. Yes, next one is Kolb's reaction. Kolb's and Riemer-Tiemann reaction will be joining adjacent to each other. That is first Kolb and first Riemer-Tiemann reaction, then Kolb's reaction, in which Kolb's reaction will be getting salicylic acid and Riemer-Tiemann reaction will be getting salicylaldehyde. That is why they are like both in adjacent or nearby. We can say they are in nearby. Okay, now this reaction will be introducing a carboxylic group, that is COOH group to the benzene ring. That is what Kolb's reaction. And note down the reagent. What we will be getting? Sodium phenoxide. First of all we will be converting alcohol to a sodium phenoxide, that is NaOH. I will be making sodium phenoxide, and this sodium phenoxide on treating with the CO2 gas in presence of acidic medium. What I will be getting? OH. This ONA will be replaced by OH, and an acidic group will be inserted into the ortho position, in which we will be calling it as salicylic acid. We will be calling it as salicylic acid. Yes. So this is all about Kolb's reaction. Then Kolb's reaction and Riemer-Tiemann reaction. One is salicylaldehyde, another one is the formation of salicylic acid. Done, everyone? Noted down everything? Don't forget these two reactions and the reagents. Shall I? Okay. If you have done writing or noting down the points, just let me know. And note down the temperature that you will be using is 400 Kelvin. Temperature that we are using is 400 Kelvin, and pressure we will be using is 4 to 7 atm. High pressure and high temperature will be required for inserting CO2 into the benzene ring. Okay, moving to the next. Okay, other essential reactions of phenol. This is very important one. Other essential reactions of phenol. Okay, I will be going through each of everything one by one. First of all, I will be doing the nitration reaction. Nitration. In the case of nitration, I am taking phenol. And what is the property of phenol? Is it activating the benzene ring, or it will be deactivating the benzene ring? Phenol. What is the nature? What is the nature of phenol? Activating or deactivating? What is the nature of phenol? Activating or deactivating? You know it, right? Okay, phenol, it is an activating group, and as it is an activating group, if I am treating phenol with a concentrated, not concentrated, I am taking dilute HNO3. If I am taking dilute HNO3, I will be inserting NO2 group into the phenol, and as it is an activating group, we will be getting ortho para product. We will be getting ortho para product. It is ortho para directly, and the first product that we will be getting is ortho nitrophenol, and the second product we will be getting is para nitrophenol, and this is ortho nitrophenol, and this is para nitrophenol. Now in this case, which one is more stable? That is another question. Which one is going to be more stable? Anybody have idea which is going to be more stable? Which is major one and which is a minor one? Which is major one and which is minor one? Normally we will be thinking that para is going to be the major one, but here ortho is the major one. Why ortho is major one? Because there is intramolecular hydrogen bonding. There is intramolecular hydrogen bonding. Due to that, this is going to be the major one. And here in the case of para nitrophenol, it is having intermolecular hydrogen bonding. As it is having intermolecular hydrogen, this is the minor one. Okay, and because of its intramolecular hydrogen bonding, what about the acidity? Will it be having higher acidity or lower acidity? It will be having lower acidity, because this hydrogen is involving in the hydrogen bonding, in which hydrogen won't be able to release as proton immediately. So the acidity will be less. It will be having less acidity, and para will be having more acidity comparing to the ortho. Okay, now if I am comparing the melting point and boiling point, if I am comparing the boiling point of ortho nitrophenol and para nitrophenol, due to intramolecular hydrogen bonding, it will be having low boiling point. And due to intermolecular hydrogen bonding, para nitrophenol will be having high molecular mass, so it will be having high boiling point. These are the points I want all of you to take a note of in the case of nitration reaction. Only whenever I am giving dilute HNO3. Now we can discuss what is the product we are getting if I am giving concentrated HNO3. Yes, if I am giving concentrated HNO3, you can see OH concentrated HNO3. As this, we already know that OH group is a highly activating group, and if I am using concentrated HNO3, there will be release of more NO2 electrophile. Which result in the formation of 2,4,6 trinitrophenol. 2,4,6 trinitrophenol we will be getting, which we will be calling by the name picric acid. Note down this point, that is in presence of dilute HNO3, we will be getting mono nitro product. In the cases of concentrated HNO3, we will be getting trinitrophenol. Yeah, this is important point you have to note down in the case of nitration of phenol. Now we can move into the halogenation, especially the bromination of phenol. Shall we move bromination of phenol? Yeah. Bromination of phenol, the point you have to note down is bromination of phenol. And bromine can be brominated in presence of CS2 which is a non-polar. In the case of CS2, what I will be getting is phenol. Phenol is not that much activating comparing to the NH2 and all, and if I am treating Br2 in presence of CS2, the product that we are getting. What is the product that we are getting? We will be getting a monobromophenol. Monobromophenol, that is we will be getting ortho and para-bromophenol. Now instead of this, if I am taking or if I am giving bromine, if I am brominating in presence of water. Water is a polar solvent, right? Water is a polar solvent. As water is polar solvent, it will be generating more bromine ion. It will be generating more bromine cation, which result in the bromination in ortho and para position. In the resulting, we will be getting 2,4,6 tribromophenol. Resulting, we will be getting 2,4,6 tribromophenol. Got it? Got it, everyone? Got it, everyone? This is polar solvent. As it is polar, we will be getting tribromophenol. Is it clear, everyone? Yes. Shall I move? This is the point you had noted down. In this case, we will be getting monobromo as well as tribromo, depending upon the solvent we are using. But in the case of aniline, we have observed that no matter whatever the reagent we have used, we will be getting tribromo aniline only. Tribromoaniline only. What is the reason? Because aniline is a very highly activating group, plus some group. And if we want to get a monobromoaniline, what we have to do? We have to do acetylation and we have to deactivate the ring, then only we can do the monobromination. Yes. So this is the comparison that you have to do in the case of aniline and phenol. Yeah. Hope all of you got this point completely. We'll be moving into the next. That is sulfonation of phenol. Next is sulfonation of phenol. Sulfonation of phenol, we have to check for the temperature. Sulfonation of phenol will be giving different product depending upon the temperature. Not different product, the product with a different position of the substrate. Yes. Phenol on treating with the H2SO4, that is bromination. If I am doing this bromination at 25 degrees Celsius, what is the product we will be getting? We all know that we will be getting sulfonic acid. But whether we will be getting sulfonic acid at the ortho position or the para position, that is the question. At 25 degrees Celsius, we will be getting SO3H attached at the ortho position. And if I am giving the temperature 100 degrees Celsius, if the temperature is higher, then the major product that we will be getting or we will be obtaining is para product. Para is a major one. Why ortho is the major one in the temperature 25 degrees Celsius? Because it is kinetically controlled. At lower temperature, the reaction is kinetically controlled. In the next case, it is the thermodynamic product. At a higher temperature, it will be following the thermodynamic product. So these are the two different product or different major product we will be getting in the sulfonation of phenol. Check for the temperature. Yes. So yeah, sulfonation of phenol is over. Now we will be moving into the acidity of phenol. When I am talking about acidity of phenol, the point that you have to note down is acidity order of orthonitrophenol, paranitrophenol and metanitrophenol. Anyhow, you know that this NO2 group, which is an electron withdrawing group, or it is a minus M group, it will be increasing the acidity by increasing the stability of conjugate base. Now we can compare the stability of the conjugate base here, and thereby we can understand the acidity order of orthonitrophenol and paranitrophenol and metanitrophenol. Okay, ortho, meta and para. My question is to you, what is the order of acidity? Ortho, meta or para, which one is more acidic? Orthonitrophenol, metanitrophenol or paranitrophenol, which is more acidic? That's my question.
Ortho.
Ortho is more acidic, sure. Ortho is more acidic, are you sure?
Para.
Para, yes, we can go through it. So here one of the important points that I have discussed few minutes before, that is hydrogen bonding. Due to the hydrogen bonding, the orthonitrophenol, we expect that it will be having higher acidity, but it won't be having the higher acidity. Because of hydrogen bonding, intramolecular hydrogen bonding, the hydrogen won't be losing immediately or easily. So before going to this, we can check what is the group that is attached. Here the group attached is minus M group, and here what is the group that is attached? Minus M or which any other effect? NO2 group. What group it is? Minus M, minus I, plus I. What group it is? Anybody? What it is? We will be thinking it is minus M. It is not minus M because mesomeric effect won't operate. We all know that mesomeric effect won't operate at the meta position. So here NO2, here it will be acting as minus I group. Minus I group. Now here the NO2 will be acting as minus M group. So among these first one, second one and third one, which is having highest minus M power, or which is having highest minus power, that is for ortho and para. So among these, ortho and para will be having higher acidity comparing to the meta one. Now when we compare ortho and para, we can see that in the case of ortho, the NO2 group is very near. So we will be expecting that it will be having highest acidity, but not. Because of the hydrogen bonding, this hydrogen won't be released easily, which result in the lesser acidity comparing to the para. So the order is para is greater, then ortho, then comes our meta. This is the order or point you have noted down. Very good, Sakshi. Yeah, you said it correctly. Shall we move? Have you got the idea about acidity of orthonitrophenol, paranitrophenol and metanitrophenol? Yes, thank you. Yes. So these are the few more. Okay, before going to one more point, I just want to note down one of the oxidation of phenol, that is by using Na2Cr2O7 OH. If I am treating oxygen Na2Cr2O7 in presence of H2SO4, the phenol will be oxidized to benzoquinone, parabenzoquinone. Note down one of the oxidation reaction of phenol. This came in the previous year NEET exam. Okay, moving to the comparison. Yes. So these are the important reactions we have discussed so far. First one is Riemann-Trimer reaction, in which reagent we have used is CHCl3 NaOH, then quartz CO2 NaOH is a reagent which will be giving salicylic acid. RTR reaction will give salicylaldehyde. Now the zinc dust, using zinc dust, this we discussed in the hydrocarbon chapter. Benzene, phenol if I am treating it with zinc in presence of temperature, what I will be getting? I will be getting benzene. And then Na2Cr2O7 bar H2SO4, just we have discussed, that is oxidation reaction, that is parabenzoquinone. For above one is reduction, the lower one is oxidation. Note down all these important reactions. Shall I move, students? I think I can move. If you have done, let me know it. Just take a copy or screenshot. Shall I move? Yes, thank you. Okay, now the last one we will be discussing in this chapter is ethers. Yes, first is preparation of ether. The first method of preparation of ether is from alcohol, that is by dehydration of alcohol, and the reagent we will be using is H2SO4. Temperature for 13 Kelvin. Only we will be getting the ether. If the temperature is 413, we will be getting ether. That is, I will be taking 2 molecules of alcohol. CH3 CH2OH. This is the first molecule, and another molecule is CH2 CH3. What I will be getting? Just remove the water and combine these two. H2SO4 under 4 13 Kelvin temperature. We will be getting diethyl ether CH2 O CH2 CH3 diethyl ether we will be getting. Okay. Now what if I am changing the temperature? Instead of this, if I am doing the same reaction at 443 Kelvin. Just let me check the temperature. Yes, 443 Kelvin. In this case, what is going to happen? Here, elimination will be taking place. And resulting will be getting an alkene. Yes, very good. CH2. 2 molecule of alkene will be getting. It's a temperature dependent reaction. If the temperature is 413 Kelvin, then only we will be getting ether. If it is above that, or if it is 443, we will be getting alkene. Got it, everyone? Temperature control is very critical here. And yes, and this method of preparation is suitable only for primary alcohol. So whenever you are doing this reaction, choose primary alcohol, then only we will be getting ether. Yes, shall I move? Have you noted down? Did you note down? Okay. Now next, the important one, Williamson ether synthesis, the important method of preparation of ether, that is by Williamson ether synthesis. In Williamson ether synthesis, alkyl halide will be converted to alkoxide, sodium alkoxide, and it will be giving ether. And note down, it is following SN2 pathway. As it is following SN2 pathway, the alkyl halide we are using, it should be primary. We already discussed in yesterday's chapter, that is haloalkanes and haloarenes chapter. Primary alkyl halide will be giving SN2 mechanism, that is less steric hindered compound will be giving SN2 mechanism, and the more steric hindered will be going through SN1 mechanism. If I am instead of primary alkyl halide, if I am using secondary alkyl halide or tertiary alkyl halide, what is going to happen? The elimination will be taking place. Instead of substitution, elimination will be taking place, resulting in alkene. Okay. Yes. So the point you have noted down, these are the point you have noted down. I will be giving an example. That is, if I am taking alkyl halide RX plus sodium alkoxide. This is sodium alkoxide. What is going to happen? This will be removed. NaX will be removed, and RO. They will be combining, resulting in the formation of NaX. And note down, we have to use primary alkyl halide here. Clear? Okay. Now there is only condition is we need to keep the alkyl halide as primary alkyl halide, but we can change the sodium alkoxide. We can change the sodium alkoxide to secondary as well as tertiary. Yeah, let me give you a reaction like that. R. Okay. O minus A plus. Here, if I am just doing, I am taking tertiary alkoxide and then primary alkyl halide. Here, I will be getting tertiary. I will be getting a tertiary ether. O R plus NaX. I will be getting tertiary ether. But instead of this, what I am doing is, if I am just taking CH3 X, if I am taking tertiary alkyl halide and tertiary alkyl halide I am taking, and primary alkoxide. What is going to be the product here? What is going to be the product? What is the product we will be getting here? Let me know. What is the product? Yeah, alkene will be getting here. One of the hydrogen will be taken by what? Taken by this oxygen, and resulting will be getting an alkene. CH3 C CH3 double bond CH2 and resulting in the elimination of halogen, and plus this oxygen will be taking proton from here, plus CH3OH, we will be getting alcohol as well as alkene here. Okay, so this is the point you have noted down for the Williamson ether synthesis. It is following SN2 pathway. So primary alkyl halide, that is the substrate that you have to use here. Is it clear completely? Shall I move? Williamson ether synthesis, don't forget these reactions and mechanisms and everything. Okay. Now the last part of this one, that is chemical reaction of ether. That is the main important one, is cleavage of ether by hydrogen iodide. We can see that cleavage. Okay. First, in the case of primary or secondary alkyl group, if I am taking primary or secondary alkyl group in the ether, then the halide, that is I minus, will be attacking the smaller or lesser hindered alkyl group. I will be giving the reaction. Suppose I am taking CH3O CH3 CH2. This one on treating with the hydrogen iodide. You know that there is a proton H plus here, I minus here. The lone pair will be attacking on the proton, resulting I will be getting a protonated ether. OH CH2 CH3. Okay. Now there will be a positive charge here. Now to stabilize this positive charge, what is going to happen? The splitting will be, or the cleavage can take place either from here or from the second bond. In this case, which one can be less sterically hindered carbocation? Which carbocation will be less sterically hindered? The cleavage will be taking place in that direction. Here this one is a 0 degree, this one is a secondary one. So here the cleavage will be taking place from this carbon to oxygen, resulting in the formation of CH3 plus, then we will be getting alcohol, that is CH3 CH2 OH, and I minus will be attacking on this carbocation, resulting in the formation of CH3I. Okay, got it everyone? Yes. Now if you want, I can give one more examples. CH3C CH3 O CH2 CH3 Okay. Now in this case, tell me which one is going to be the major product, or where the I minus will be attacking. Here the first step is this lone pair will be attacking on the proton, resulting in the formation of a protonated. Okay, just I will be writing it a little bit lower part. CH3 C CH3 O CH2 CH3. Lone pair will be attacking on the hydrogen. What I will be getting? CH3 C CH3 OH with a positive charge, CH2 C3. Now my question is, where there will be cleavage, how the cleavage will be taking place. This is the first cleavage, it can take place from here to here. This is the first one, and second one is like this, second one. Which cleavage is going to take place, first one or second one?
Second.
Yes, very good, second one, because second one cleavage only will be forming a carbocation which is less sterically hindered. So the second cleavage is the correct one, and the remaining one we will be getting an alcohol, OH plus CH2 plus CH3. Okay, and then I minus will be attacking on this carbocation, resulting in the formation of CH3 CH2I. Okay. Yes, this is the point you have noted down in the case of primary and secondary alkyl groups. if there is a primary and secondary alkyl group in either, this is how the cleavage will be taking place. That is, cleavage will be taking place in that direction where I minus can attack on the less sterically hindered carbocation. Got it? Got it, everyone? If you are done, you can give me a thumbs up. Thank you. Okay, now next one, if there is a tertiary alkyl group, if one is tertiary alkyl group, then it will be following SN1 mechanism. Previous one, primary and secondary, it is following SN2. So here, if there is at least one alkyl group is tertiary. If one is tertiary, then what is going to happen? First step is protonation. Yeah. Okay, now my question is how the protonation will be, how the cleavage will be taking place here. First one or second one? This is first one and this is second one. How the cleavage will be taking place? First or second?
First.
First one, very good. First one cleavage will be taking place. Why? If there is tertiary, then the reaction will be moving in that direction where I minus can attack on the more stable carbocation. Carbocation here plus CH3OH. I got alcohol. Now this carbocation will be reacting with what? Will be reacting with the I minus and we will be getting tertiary alkyl iodide. Okay, this is the point you have noted down in the case of tertiary group present in either. Got it? Not only this one, not only tertiary carbocation, if you are getting allylic or benzylic carbocation, then at that case also, if you got an alkyl halide which is primary allylic or secondary allylic or benzylic, in that case also you have to go in SN1 mechanism, in which I minus will be attacking on the more stable carbocation. Okay, in this case also you have to attack the I minus on this carbon, benzylic carbon. Got it? Got it, everyone? Yes. This is the complete idea about this chapter, alcohol, phenols and ether. Now just I want to, okay, one more point is there, that is about the electrophilic substitution of anisole. That is in the case of ether. Okay, anisole, we all know that anisole, this is what anisole, or CH3, electrophilic substitution of anisole. This anisole, it is electron donating group or electron withdrawing group. Is it activating or is it deactivating?
Electron donating group.
Electron donating group. As it is an electron donating group or as it is an activating, they are ortho-para-directing or meta-directing? Ortho-para-directing or meta?
Meta.
Yes, very good. It's a meta. Sorry, how come it is a meta? How come it is a meta? Activating group are what? Ortho-para-directing or meta? Just think. What it is? Activating groups are ortho-para-directing. Ortho-para-directing. As it is ortho-para-directing, if this anisole on treating with, if it is undergoing halogenation, that is Cl2. If it is undergoing halogenation, what is going to be the product? OCH3, I will be getting Cl in the ortho-para position. Ortho-para position. Now if I am doing the nitration, what is electrophile? I will be getting NO2 plus, and this NO2 plus is also ortho-para-directing. And if I am doing sulfonation, SO3H, sorry, H2SO4, H2SO4, the electrophile that is forming is SO3. SO3 is electrophile, and what is the product we are getting? SO3H plus SO3H in the ortho and para. Then comes which one? Friedkraft alkylation, Friedel-Crafts alkylation. Friedel-Crafts alkylation, if you observe, the carbocation will be getting, that will be attaching. And if it is Friedel-Crafts acylation, which is the electrophile, that will be forming ortho-para or C double bond O plus. So just attach this in the ortho and para position, you will be getting. So this is the complete idea about electrophilic substitution reactions of anisole. It is ortho-para directing because OCH3 is an activating group. Got it? All of you know, just know what is the electrophile in this and attach that into the ortho-para position of benzene. That's the only thing you have to do it. Got it, everyone? Shall I move? Shall I move, my dear students? Yes, thank you. Now the things are over. Alcohol, phenols, ethers, all the important reactions we have covered here. Now just to note down some comparison. If I am looking into the alcohol, phenols and ether, while comparing boiling point, you can see alcohol is having, alcohol and phenol both are having high boiling point. What is the reason? Because of hydrogen bonding. Ether will be having low boiling point. Now coming to the solubility. You can see alcohol and phenols. Alcohol is more soluble in water. Phenol is partially soluble, and ether is generally insoluble because ether is, we know that it is a non-polar. Then coming to the acidity, alcohol is weak acidic, then phenol is weak but not that much weak comparing to the alcohol, because in the case of phenol, the phenoxide ion is stabilized through resonance. Then ether is neutral. Now the test we will be using to detect alcohol. First one is Lucas test, another one is Victor-Meyer test. That is to distinguish primary, secondary and tertiary alcohol, which we already have discussed. Now the phenol. Coming to the phenol, one of the tests that we will be using to detect the presence of phenol, which we already discussed in the mock paper discussion. Hope all of you are remembering that. That is neutral FeCl3. If I am treating neutral FeCl3 with a phenol, I will be getting a violet color which indicates the presence of phenol. And either normally will be distinguishing by using HI cleavage. HI cleavage, you know, right? If it is tertiary, then we will be getting tertiary alkyl iodide. Secondary and primary, it can be distinguished by checking which carbon the I minus is attaching. Okay. So this is all about the alcohol, phenols and ether. Now we can move into the questions. We can move into the important questions that is comes in the previous year. First one, all of you go through it and just give me the answer. Are you clear about this chapter? Do you have any doubt, or anybody want me to take any particular portion of this chapter, or shall we directly move into the PYQ? Organic, more you have to focus on PYQ. If you see, like, there are the toppers, majorly the toppers, if you observe, they will be, before going into the, just having an understanding of this chapter, they will be immediately diving into the PYQs. So organic, you can go more with the questions, and thereby you can get more clarity of the concepts. Okay. Yeah, what is the answer for this first question? CH3OH. CH3OH. If you observe organic, yeah, option C. Yes. Option C. Okay, we can see it. I am also not sure. I will be going through reaction and I will be getting the answer. Organic, if you observe the questions, you won't be getting from a single chapter. It will be a mixture of chapter. CH3OH will be treating with SOCl2. What is this? Substitution. That is haloalkanes and haloarenes chapter. SOCl2. Darson's process in presence of pyridine. CH3Cl. Now this one on treating with the KCN in presence of aqueous ETOH. What it is? Again substitution. CH3Cn. And then it one treating with the sodium amalgam in presence of ETOH. What is this reaction called? This we discussed in, this we have discussed where we have discussed this one. This we have discussed in the amines chapter, in which this reaction is called as Mendes reaction, in which we will be getting amine CH2 NH2. Now the last one, this one on treating with the NaNO2 diazotization and HCl in presence of water. We know that primary amine on diazotization, the product is very unstable. It will be immediately converted to alcohol. Yes, you are correct. Very good. So this is the complete. You can see the questions are from different chapters. Yes. Hope it is clear. Shall we move to the next question? Can I move to the next question? Yes. Yes. Here is the next question. Go through it. Yeah, CH3 CH2OH. Phosphorus plus iodine. Then on treating with the magnesium in presence of dry ether, you will get B. Then HCHO, formaldehyde, will be giving C, which on hydrolysis will get the product D. What is the product D? Go through, it's very easy only. Phosphorus plus iodide, what I will be getting? Yesterday we have discussed this one. PI3 will be getting, which is a substitution reaction. CH3 CH2 OH, CH3 CH2 I, and then on treating with the magnesium, presence of dry ether.
Option A.
Option? What is the option?
A.
Option, yeah, let me check it. Option A, yes, very good. Very good, option A. Now dry ether magnesium, what we will be getting? This is a Grignard reagent, right? We will be getting a Grignard reagent when magnesium treated with the alkyl iodide. So CH3 CH2 MgI. Now the next one. This one on treating with HCHO. Grignard reagent on treating with HCHO. This negative will be attacking on this carbon. There will be shifting of this bond, resulting in the formation of CH3 CH2CO minus CH2O minus. And this one on adding water, I will be getting N-propyl alcohol. Yes, very good, it's correct. Go through the complete reaction and get an understanding. Can I move to the next question? Yes, moving to the next question. Yes, which one of the following alcohol react instantaneously with Lucas reagent? And another easy question. Lucas reaction already you know, it will be giving immediate reaction with the tertiary alcohol, then secondary, then primary, as it is following SN1 mechanism. Yeah, what is the answer?
Option D.
Option D, very good. Tertiary alcohol, this is tertiary, so this will be giving Lucas test immediately. Now the next one. Product A and B obtained in the following reactions respectively are. I think the same thing we discussed in the haloalkanes. Option?
D.
Option D, very good. Option D. Here one thing is that both the cases you will be getting alkyl halide, but you should know about the byproduct also. Yesterday I have said you that is if PCl3 reacted with the oxygen containing substrate, you will be getting H3PO3 as the byproduct, and PCl5 on reacting with the oxygen containing substrate, you will be getting POCl3 as the substrate. Yes. Next one. Yeah, go through it. It's a NEET 2024 question. The major product A and B in the following reaction. PBr3 on treating with alcoholic AOH. Are we did the same question yesterday? What is the answer? A, B, C, D. What's the answer? How will be solving this question? CH3 PBr3. Of course, what we all know that it is a substitution reaction in which the OH group is substituted. Okay, now this one on treating with the alcoholic AH. What alcoholic AH will be doing? What alcoholic AH will be doing in presence of temperature? Yesterday we discussed about it. What alcoholic AH will be doing?
Alkene.
Yeah, it will be giving alkene, which will be undergoing substitution reaction. That is alpha beta elimination. Okay, there is no cyclic ring, right? Okay. Yes. Yeah, this is alpha and this is beta. Alpha beta elimination will be taking place and resulting in the formation of a more stable alkene. So what is our final product? Question A. What is answer A? This is answer A. And option answer B. What is answer B? Yes. Yes, option A is the correct one. Got it, everyone? Shall we move to the next question? Yes, thank you. Yeah, here is another question for you. Consider the following reaction and identify the product. Yes, identify the product here. HBr addition to an alcohol. HBr addition. Option D. Are you sure? Yes, option D is the correct one. It's a very easy question only. This we already have discussed in the previous classes. That is HBr addition to an alcohol. What is going to happen here? What is going to happen? Yeah, OH. That is H plus will be attacking on the hydrogen, which will be releasing the water, resulting in the formation of a carbocation. We can directly follow the Markov-Nikov rule here, but we have to check for the rearrangement of carbocation. But this is secondary carbocation. It can rearrange itself to tertiary carbocation. And into this tertiary carbocation, the Br minus will be attacking. Br minus will be attacking and resulting in the formation of CH3, CH3, Br, CH2, CH3. Okay, here is how you have to find out the answer for it. Yes, shall I move to the next one? Yeah, here is another question for you. Consider the following reaction. Cleavage of either by HI. Find out the product. Already I have discussed this one also, this one in the class. A, B, C, D. What's going to be the answer? What's the first step? First step is this oxygen will be attacking on the hydrogen. What I will be getting here? CH2 OH, CH2 OH with the positive charge. Now how the splitting will be taking place, or how the cleavage will be taking place here? How the cleavage will be taking place here? First one or second one? First one or second one? Which cleavage will be taking place here? That's my question. Which cleavage?
First.
Yes, very good. First one. What's the reason? Because first cleavage will lead to a stable benzylic carbocation, and the second one won't be giving that one, because positive charge on benzene is a unstable one, so it will be giving phenol. And this one not rating with I minus, I will be getting benzyl iodide. Got it, everyone? Shall I move? Yes. Which among the following will be most readily dehydrated under acidic condition? More readily dehydrated under acidic condition. Which one will be more easily dehydrated is the one which will be forming a stable product. Normally we know that alcohol on dehydration we will be getting alkene. So check among these which one can form a stable alkene. That's the question. Anybody got the answer? Shall I give you the answer? Here you can see the option A. See the option A. CH3 CH3 CH OH CH2 CH OH CH3. Look at this reagent. Now here you can see it is an elimination reaction. Dehydration, it is an elimination reaction. Alpha beta had OH from the alpha position and hydrogen from the beta position. Hydrogen from the beta position will be eliminating, and here one more OH group is there. Here one more OH group is there, and in the one more OH group you can see there is a one more beta hydrogen. Okay, now where it will be eliminating? It will be eliminating in this way. What is the reason? What is the reason? Because here on elimination, here on elimination we will be getting an alkene which is in conjugation. Yeah, that is, here you got an alkene which is involved in the conjugation, so which will be making it more stable. That is why this one will be easily undergoes dehydration. Now the remaining thing, if you observe, there is no stable product that will be obtaining here because there is only one double bond. Got it? Is it clear, Sakshi?
Yes, sir.
Yes. We'll be moving to the next question. Yes. Yeah. Tell me the answer for this one. Everything is mentioned in the table. Just you have to identify what is the reaction happening here. What is the name of this reaction? First one, NaOH in presence of CO2 H+. What is this one? What is this reagent? We already discussed this one. What is this reagent? Tell me.
Option D.
Option D. Okay, we can go into the option D. First one. This is, what is this reaction called? First one, NaOH CO2.
Salicylic acid.
Yeah, salicylic acid. Kolb's reaction. Very good. Second one, NaOH CHCl3. Salicylaldehyde. That is RTR. Then zinc dust. That also we discussed. Phenol. Yeah, phenol. Phenol on treating with zinc dust, we will be getting benzene. Then Na2Cr2O7. Oxidation of phenol. We will be getting benzoquinone. Yes. So that is my answer. Yes. Shall I move to the next question? Are you got a complete idea? Yes. Yeah. Find the answer for this one. NEET 2022 question. Which of the following reaction sequence is incorrect method to prepare phenol? Incorrect method to prepare phenol. All these things we have discussed. Yes. A, B, C, D. We need phenol. Any idea?
Option D.
Option D, yes, very good. Why option D is not going to give phenol? You will be thinking that okay, there is an OH group here, but sorry. Okay, you will be thinking there is an OH group here which can substitute here, but here there is a lone pair of electron which is involved in the delocalization, which we discussed in yesterday's class, and because of that this bond won't be breaking, so OH won't be substituting, so this is not going to give phenol. And this one, it is cumene method of preparation of phenol from cumene. And what about this one, diazonium salt, method of preparation of phenol from diazonium salt, that is benzene diazonium chloride. We'll be treating with warm water, we will be getting phenol. Now this one, what is this one? Oleum, that is benzene sulfonic acid. Benzene sulfonic acid SO3H will be treating with a NaOH and H3O plus. I will be getting phenol, which we already discussed in the class. Got it? Yeah. Now one more question for you. Given below are two statements. Acidic strength of mono-substituted nitrophenol is higher than phenol because of electron withdrawing nitro group. Electron withdrawing nitro group. What is the answer? Is it correct? Option?
Option C.
Option C. Statement 1 is correct. Yes. Nitrophenol acid strength is due to the electron withdrawing nitro group. Statement 1 is correct. What about second one? Orthonitrophenol, metonitrophenol, paranitrophenol have same acid strength. No, it is wrong. Which you already discussed that ortho is having lesser. Comparing to the ortho, nitro, and meta, which is having highest acidity? Para is having highest acidity. Then comes ortho, then meta. Yes, good. Now the last and final question for you. Yes. In Lucas test, primary, secondary and tertiary alcohol are distinguished on the basis of their reactivity with the concentrated HCl plus ZnCl2 known as Lucas reagent. Is it correct? Can I say the first statement is correct? Yeah, of course we can say it is correct, right? Yes. Yeah, that is Lucas test will be helping to distinguish primary, secondary and tertiary alcohol. They will be giving the different time reaction. Tertiary will be giving immediately. Now what about the second one? Primary alcohol are more reactive and immediately produces turbidity at room temperature on reaction with the Lucas reagent. Is it correct? Primary, is it? Yeah, it is not going to correct. Primary won't be giving a reaction with the Lucas reagent because it is very less reactive, because this reaction is taking place by SN1 mechanism. Tertiary will be giving you the turbidity immediately. Okay, so the answer is statement 1 is
C.
Yeah, option C is correct. Yes. So that's all about the today's class. Few more questions are there that I have added here. You can go through it. Solutions also I have added here. You can go through it and you can get a complete clarity of this chapter. So that's all about the today's class. Thank you all for joining, and tomorrow we'll be seeing with another chapter, that is coordination compound. All of you just go through this chapter once so that tomorrow we can go through this chapter little bit more easily. Yes, thank you all of you for joining.